Hi everybody, thanks for checking into another math video. This one is going to be about solving some nonlinear systems of equations. Nonlinear systems of equations occur in lots of different configurations, so we're only going to handle a couple here in this video. All right, first off, I should probably define what a nonlinear system of equations is, and I would say that a nonlinear system of equations is a system of two or more equations to be solved simultaneously, that is at the same time, and at least one of those equations is nonlinear. And I'm sure that's a famous quote from somebody, probably, maybe. Okay, first off, so what we're talking about here is a system of equations, that is two equations where one of them is not a line. Okay, and so for example, it could be a line crossing a parabola, and you can see that it crosses in two different places. And so the solutions to the system of equations is always equal to the number of intersection points of their graphs. It's not always necessary to think about graphs, but I think it is a very helpful way to kind of visualize what we are doing, and as a general guideline to making sure that we find all the solutions to the system. So a line in a parabola maybe, or maybe a line and a circle, each of those have two different solutions. Well, let me say they have as many as two solutions. They might have only one solution if the line just is tangent to the circle, or they might have zero solutions if the line does not intersect at all. So you could have as many as two, but you could have fewer. Or you could have something kind of crazy like this, like a parabola crossing a circle in four different places. So the thing about nonlinear systems of equations is that they always have this possibility of having more than one solution. All right, so as an example here, I thought we would take a look at this problem. You may recognize these if you've done some of the recent assignments from our class, but if not, that's okay. It's two circles. There you see the equations, both equation written in center radius form, so they're easy to visualize, and I would say that's a good thing to do. Those two circles may look something kind of like that on an XY plane, and you can see that they're going to cross in two different places. Therefore, there are probably going to be two solutions to this system of equations. All right? Okay, so once you've determined that there's going to be as many as two different solutions here, the next thing to do is to use some algebra. All right, we're going to solve this with algebra. The graphing is not a dependable way to find solutions precisely, but it is good to think about the graphs in general. So what we have to do is we have to get those two equations somehow combined together into a single equation in order to eliminate one of the variables. All right, and there are various ways to do this, but what I would like to kind of focus your attention on is that each of those equations have a common expression. They both have a y minus 3 squared in them. That common expression is often a very good place to look for a way to combine the two equations. What we can do is take each of those equations and isolate that common expression. So in a sense, we're kind of solving them for, in this case, y minus 3 squared. I'm using the word solve just to really mean isolate, okay? So we isolate that common expression, and then we can use the right side of each equation and set those parts equal to each other, all right? So this is our technique for combining the two equations into a single equation with only one variable, and now we are ready to solve for x, okay? So let's do that. You take pretty basic algebra steps here at the beginning. Subtract the 25 from both sides, multiply both sides by -1 to get rid of that negative sign there, and you've got your two squared binomials set equal to each other like that. Next step, I guess, would be to expand each of those binomials and continue to simplify the expression down. You notice that the squared parts both drop out, so we've got a linear equation now, which means that we only have one solution for x. Okay, well, geez, I thought maybe we would have two solutions, but looks like the algebra is all good, so we get one x value. Well, this x value is the x coordinate, of course, of our solution points, and now we have to find the y values. Okay, so how do we find the y values, everybody? Plug it in, right? That's what you do. You're going to plug that x value in to one of the equations, and it doesn't matter which one. Let's pick the first one. All right, so x plus 2 squared plus y minus 3 squared equals 25. And remember, x equals 1. So we're going to replace the x with 1. It's as easy as that. And so 1 plus 2 squared is 9. So we can expand out that other binomial there and kind of simplify things down to a nice little quadratic in standard form. And hallelujah, it's factorable. All right, so we're going to get some nice integer values for y. And we know that x equals 1. And now we know that y equals 7 and y equals negative 1, which means that those two coordinate pairs, 1, 7 and 1, negative 1, are the solutions to the equation. Let's have a look at the graph again, see if that sort of jives with our original estimate there. And yeah, that looks pretty good. It does make sense, actually, that the two circles have the same x value for both of their intersection points. Okay? If you think about the geometry there, about those circles and where they're located, hopefully that will make sense. All right, so think about that for yourself if you need to, but there you go. There's our solutions. All right, we're done. Let's try another one. This time, let's try a line and a parabola. All right, so 2x minus 3 and x minus 4 squared plus 5. Okay, so just a real quick sketch of those two things. A line crossing a parabola, it looks like it could have two solutions here. Okay, so we'll sort of aim for that. And you can see in this case, they're both set equal to y. So I can just rewrite the right side of those equations equal to each other. That's our common expression, right? This one's kind of already set up for that, whereas the previous example, we had to do a little bit of work to get that common expression isolated. So there you go, 2x minus 3 equals that, and I've already expanded that binomial there. And now just to kind of keep going with our basic algebra maneuvers there to simplify the equation into standard form. And yes, indeed, this one also is factorable. Let me just comment on that. If it was not factorable, you could still do this. You would have to use maybe completing the square or maybe even the quadratic formula to continue your to continue finding the solutions. One way or another, you have to find the solutions to that equation, and those are your x values, okay? This one, we get nice integers, x equals 6 and x equals 4, and remember, we do have to use each one of those. We have to use both of them to find the y coordinates, okay? This time they're different. So let's take that top equation there, that linear equation, and replace the x with 6. So when x equals 6, that's 2 times 6 minus 3, 12 minus 6. So that makes y equal to 9. So that means the point 6, 9 is one of our solution points. If we've done all the algebra correct, that is one of our solutions. Let's try this again with the other x value, x equals 4, and 8 minus 3 is 5. So that means when x equals 4, y equals 5. And yes, indeed, the algebra checks out. That is the solution to that, those are the solutions to that system of equations. Two intersection points, and there's the coordinates for each one of those points. Okay, good. Well, let's just generalize now some of the tips that we've been talking about here in this video. First thing, I think it's a good idea to consider how many solutions are possible for your system of equations. Your ability to sketch graphs quickly will help you there. I don't say it's absolutely necessary, and I certainly wouldn't recommend always graphing just to find those solution points. They might be integer numbers, but they might not be, and graphs are not so good for finding those non-integer intersection points. You want to depend on your algebra to find those solutions ultimately. But the graphs give you kind of a general idea of how many solutions are possible. Then you have to find some way, and you might have to get creative, but you have to find some way to get those equations combined together into one equation where you can eliminate one of the variables. Because as you know, you can only solve an equation if it has one variable. All right, and then finally, you just want to make sure that you include the x and y coordinates of all the solutions. And if you do all of that correctly, double checking your work and everything, you're done, and you'll have a good outcome to your work. All right. So once again, thanks very much for watching, everybody. I hope you're doing well. All right. Be calm, be cool, and do good math. All right. Take care. Bye-bye.